Good morning students. Today we are going to see the next point from the chapter the crystalline state, that are the symmetry operations. Symmetry operations are related to the symmetry present in a crystal. As we know that if we consider a human body, then it is a bilateral symmetry. It means that from a center of a body of a human, there is one axis which is passing, and if we cut the human body along this line, then it will get distinguished or differentiated into two equal parts, and hence we are considering human body as a bilateral symmetry. Such type of symmetries are present in crystal also, and all these operations related to symmetry present in a crystal, they are named as symmetry operations. There exist certain operations which when operated on a given structure, the structure remains unchanged or invariant. Such operations are called symmetry operations, and the structure is said to have symmetry under such operations. There are different types of symmetry operations present in a crystal. These are translational symmetry, rotational symmetry, symmetry under reflection symmetry, and inversion symmetry, that is center of symmetry. Let's see what are these. Translational symmetry. We know that in a crystal there is a regular periodic arrangement of atoms in three-dimensional space. Suppose I consider a two-dimensional crystal lattice, then its length is along x-axis is represented by A, and along y-axis it is represented by B. If I want to extend this crystal or this lattice, then I have to translate A along x-axis infinite times and B along y-axis infinite times, and such type of symmetry is called as translational symmetry. We can translate the entire crystal structure by translational operation. Then rotational symmetry. If we rotate the crystal to certain degree, then crystal will match with itself, and such type of symmetry present in a crystal is called as rotational symmetry. There are also reflection symmetries. It means that if we consider a plane and if we take the image of crystal along this plane, then crystal will match with itself, but it will be the mirror image of that crystal. It means that it will remain invariant, and such type of symmetry is called as reflection symmetry. Then there is one more symmetry, it is called as point symmetry, center symmetry, or center of inversion. In a crystal, such one center of inversion is present. Now symmetry elements. Let's define symmetry elements. The definite order arrangement of faces and edges of a crystal is known as symmetry elements. The main symmetry elements in crystalline solids are named as center of symmetry, axis of symmetry, and planes of symmetry. Let's consider center of symmetry first. This figure 4.30 shows us center of symmetry. Center of symmetry is a point which is located or present at the center of body of a crystal, such that if we draw a line passing through this point, then it will join similar points on crystal surface. Therefore, this is called as center of symmetry. It will divide the crystal into two parts along this line if we cut the crystal. And in every crystal, only one such center of symmetry exists. Therefore, its quantity is 1. Then axis of symmetry or rotational axis. It is a line passing through a crystal such that if we rotate crystal along this line, then crystal will match with itself. That is, it's a line. So remember, center of symmetry is a point and axis of symmetry is a line. Then crystal will comes to congruent position or self-matching position if we rotate crystal along this line. In order to find the number of axes of symmetries present in a crystal, Suppose we rotate a crystal through 360 degree divided by total number of rotations n, then crystal will match how many times. That will gives us quantity of axis of symmetry. In order to find that, let's substitute n is equal to 1. When we substitute n is equal to 1, 360 degree by 1, it comes out as 360 degree. It means that if we rotate a crystal through 360 degree, then it will match with itself. This is called as self-coincidence, and such axis is called as identity axis. Then next is diad axis. Suppose I substitute n is equal to 2. It means that 360 degree divided by 2, that is 180 degree. It means that in a complete rotation of 360 degree, if I rotate crystal through 180 degree, it will match with itself once. Again I rotate it through 180 degree, it will match with itself again. It means that in a complete rotation of 360 degree, crystal is going to match twice with itself. Therefore, this axis is called as two-fold axis of symmetry or diad axis. In order to find its quantity, one should know diad axis passes through opposite edges, and we know that cube has 8 corners, 12 edges and 6 faces. Therefore, the diad axis passes through opposite edges. Therefore, number of diad axes present is equal to 6. And figure C shows such type of diad axis. There we have rotated the crystal through 180 degree for self-coincidence. Then next, triad axis. For triad axis, you have to substitute n is equal to 3. By substituting n is equal to 3, 360 degree by 3 gives us 120 degree. It means that if we rotate crystal through 120 degree, then it will match with itself. And in a complete rotation of 360 degree, we will obtain such position thrice, and hence it is called as three-fold axis of symmetry or triad axis. We know that triad axis passes through body diagonal, and cube has 4 body diagonals. Therefore, the number of triad axes comes out as 4. Figure B shows such type of triad axis where we have rotated crystal through 120 degree for self-coincidence. The next is tetrad axis. In order to find tetrad axis, let's rotate the crystal through 360 degree 4 times. It means that if we rotate the crystal, if we substitute n is equal to 4, that is, if we rotate the crystal through 90 degree, then it will self-match with itself or comes to congruent position 4 times. After each interval of 90 degree, it will match with itself, and hence such type of axis is called as four-fold axis of symmetry or tetrad axis. In order to find tetrad axis, one should know the tetrad axis passes through opposite faces. Just now I have told that cube has 8 corners, 12 edges and 6 faces. If there are 6 faces, then tetrad axis passes through opposite faces. Therefore, their quantity comes out as 3. Therefore, number of tetrad axes present in a cube is 3. And figure A shows such type of tetrad axis. Then last is plane of symmetry. What is plane of symmetry? Plane of symmetry is a mirror plane which is passing through crystal such that it will divide crystal into 2 equal parts, and each part will be the mirror image of other. So, if we consider the planes of symmetry present in a crystal, we will distinguish them into 2 types, that is straight planes and diagonal planes. Straight planes are the planes which are passing through opposite faces, and diagonal planes are passing through body diagonal. Straight planes are passing through opposite faces. There are 6 faces present in a cube. Therefore, the quantity of straight planes will come out as 3. Therefore, cube has such 3 straight planes of symmetry. Then next, Diagonal planes. In case of diagonal planes, and figure ABC shows these three planes, straight planes of symmetry present in a cube. In a figure 1, it is a plane passing through opposite faces vertically, horizontally, and this is also one of the section where we are getting a straight plane of symmetry. Then diagonal planes. The figure A, B, C, D, E, F, which is beneath of this figure, these are showing the diagonal planes of symmetry. They are passing through body diagonals. Therefore, in crystal, there are total 9 planes of symmetry. So, diagonal planes are 6 in number and straight planes are 3 in number. Total number of planes of symmetry are 9. Therefore, if we collectively look at the scenario of symmetry operations, then center of symmetry 1, straight planes of symmetry 3, diagonal planes of symmetry 6, that is total planes of symmetry 9, tetrad axis 3, triad axis 4, diad axis 6. Therefore, cube has total 23 symmetry operations or elements. Thank you.